4 billion miles from Earth, floating at a gravitational balance point between our planet and the Sun, the James Webb Space Telescope is quietly revolutionizing our understanding of the cosmos. Since beginning its observations in 2022, this engineering marvel has peered deeper into space and further back in time than any instrument in human history. What it has discovered challenges many of our assumptions about how the universe evolved and raises profound questions about our place within it. From impossibly large ancient galaxies to the chemical signatures of potentially habitable worlds, Webb's revelations are rewriting astronomy textbooks and forcing scientists to reconsider fundamental theories about cosmic evolution. The journey to Webb's current position at the second Lagrange point represents one of humanity's most ambitious engineering achievements. The telescope's deployment required a precisely choreographed sequence of over 300 critical steps, each of which had to work perfectly for the mission to succeed. Unlike its predecessor Hubble, which orbits Earth at a distance of just 340 miles, Webb operates in the frigid depths of space where temperatures plummet to negative 370 degrees Fahrenheit. This extreme cold is actually essential for Webb's mission, as it allows the telescope's infrared instruments to detect the faint heat signatures from objects that formed when the universe was in its infancy. The telescope itself represents humanity's most ambitious attempt to understand the universe's deepest mysteries. With its massive 6.5-meter golden mirror, composed of 18 hexagonal segments, each precisely aligned to within billionths of a meter, Webb can collect light that has traveled for over 13 billion years to reach us. The mirror's gold coating isn't just for appearance. Gold is highly reflective to infrared light and doesn't tarnish in the vacuum of space, making it ideal for Webb's mission to observe the infrared universe. The telescope's suite of 4 scientific instruments can analyze this ancient light with unprecedented precision, breaking it down into its component wavelengths to reveal the chemical composition, temperature, and motion of objects across cosmic time. Unlike the Hubble Space Telescope, which primarily observes invisible light, Webb's infrared vision allows it to see through cosmic dust and capture light that has been stretched to longer wavelengths by the universe's expansion. This capability has opened entirely new windows into cosmic history, revealing epochs that were previously invisible to human observation. When light from the most distant galaxies began its journey toward us, the universe was much smaller and hotter than it is today. As space itself expanded over billions of years, this light was stretched from its original blue and ultraviolet wavelengths to the infrared part of the electromagnetic spectrum that only Webb can detect with sufficient sensitivity. The most startling discovery Webb has made involves the early universe's unexpected maturity. When astronomers first turned the telescope toward the cosmic deep field, peering into a patch of sky that appears empty to other telescopes, they expected to find primitive, small galaxies struggling to form their first stars in an era when the universe was still cooling from the Big Bang's aftermath. Instead, Webb revealed a cosmos that achieved remarkable complexity much earlier than anyone predicted. Massive galaxies with well-organized spiral structures, actively feeding supermassive black holes, and robust star formation were already thriving when the universe was less than 1 billion years old. These findings suggest that the processes that shape cosmic structure operated far more efficiently in the early universe than our models predicted. One of Webb's most significant discoveries involves galaxies that appear impossibly massive for their age. The telescope identified what is currently the most distant known galaxy, JWST 14-0, seen as it existed just 290 million years after the Big Bang. This ancient system appears remarkably bright and extended, suggesting it contains hundreds of millions or even billions of stars, despite existing during a period when galaxies should have been small and underdeveloped. The galaxy's spectral signature reveals active star formation and the presence of heavy elements that should have taken much longer to accumulate through successive generations of stellar birth and death. To understand why this discovery is so significant, consider the timeline of cosmic evolution. The Big Bang occurred 13.8 billion years ago, creating a universe filled initially with only hydrogen, helium, and tiny amounts of lithium. The first stars had to form from this primordial material, live their lives, and die in spectacular explosions that scattered heavier elements throughout space before the next generation of stars could form with access to the carbon, oxygen, silicon, and iron that enable rocky planet formation and complex chemistry. Traditional models suggested this process would take at least 500 million to 1 billion years, yet JWST 14-0 shows signs of mature stellar populations and organized structure that challenges our understanding of how quickly cosmic architecture can form. The galaxy's very existence suggests that the universe's first billion years were far more eventful and productive than previously imagined. Star formation rates in the early universe appear to have been dramatically higher than in the modern cosmos, with some ancient galaxies creating new stars at rates hundreds of times greater than our own Milky Way manages today. This intense early star formation has profound implications for cosmic chemical evolution and the timeline for when rocky planets and potentially habitable worlds first became possible. Webb's observations have also revealed that supermassive black holes existed much earlier than traditional theories predicted. These cosmic monsters, containing millions or billions of times the mass of our Sun, are found at the centers of galaxies that formed when the universe was still in its infancy. The presence of such massive black holes so early in cosmic history poses a fundamental challenge to our understanding of how these objects form and grow. Traditional models assume that black holes start small, perhaps forming from the collapse of the first massive stars, and then grow gradually over billions of years by accreting matter from their surroundings. However, Webb's discoveries suggest they reached enormous sizes much more quickly than this gradual process allows. Some of the supermassive black holes Webb has observed in early galaxies would require accretion rates that exceed theoretical limits based on the physics of matter falling into black holes. When matter spirals into a black hole, it heats up and emits intense radiation that creates outward pressure. This radiation pressure should prevent additional matter from falling in beyond a certain rate called the Eddington limit. Yet some early black holes appear to have grown much faster than this limit would allow, suggesting either unknown accretion mechanisms or alternative formation pathways. One possibility is that these supermassive black holes formed directly from the collapse of massive gas clouds in the early universe, bypassing the stellar formation stage entirely. Under the right conditions, enormous clouds of primordial gas could have collapsed directly into black holes with masses thousands of times greater than our Sun, giving them a head start in the growth process. Another possibility involves intermediate mass black holes that formed through exotic processes in the universe's first moments, and then grew rapidly during the early epochs when matter density was much higher than today. The telescope's infrared sensitivity has also revolutionized our understanding of star formation in the early universe. Webb can peer through the dust clouds that typically obscure stellar nurseries, revealing star formation rates that were dramatically higher in ancient galaxies than in modern ones. The telescope's observations show that early galaxies were essentially cosmic fireworks displays, with intense bursts of star formation creating brilliant stellar nurseries that outshone anything we see in the contemporary universe. This intense early star formation has implications for the production of heavy elements and the chemical evolution that eventually led to planets and potentially life. Webb's ability to observe star formation through cosmic dust has revealed that many early galaxies were undergoing what astronomers call starburst phases, periods of extremely rapid stellar birth that can increase a galaxy's stellar mass by factors of 10 or more in just a few 100 million years. During these starburst events, galaxies can convert their gas supplies into stars with remarkable efficiency, creating stellar populations that are fundamentally different from the more sedate star formation we observe in modern galaxies like our own Milky Way. Perhaps most intriguing are Webb's discoveries about exoplanets and their atmospheres. The telescope's precise spectroscopic capabilities allow it to analyze the chemical composition of planetary atmospheres by observing how starlight filters through them during transits, when planets pass in front of their host stars from our perspective. Webb's first exoplanet atmospheric analysis focused on WASP 96b, a hot gas giant located 1,150 light-years from Earth. The telescope detected clear signatures of water vapor in the planet's atmosphere, along with evidence for clouds and haze, demonstrating webs to characterize exoplanet atmospheres with unprecedented precision. However, it was Webb's analysis of K2-18b that generated the most excitement in the astronomical community. This exoplanet, located 8.6 times as massive as Earth and orbiting within its star's habitable zone where liquid water could potentially exist on its surface, showed spectral signatures that included methane, carbon dioxide, and potentially hydrogen sulfide. These detections represent one of the most detailed atmospheric analyses ever performed on a world outside our solar system and mark a significant step forward in our ability to characterize potentially habitable exoplanets. The atmospheric analysis of K2-18b generated particular excitement because some teams reported tentative detections of dimethyl sulfide, a sulfur-based compound that on Earth is primarily produced by living organisms, particularly marine algae and bacteria. While these detections remain controversial, and some independent analyses found no statistically significant evidence of these compounds, the possibility that Webb might have detected biosignature gases around another world represents a watershed moment in the search for extraterrestrial life. Even if the dimethyl sulfide detection is not confirmed, K2-18b represents exactly the type of world that could potentially harbor life as we know it. K2-18b orbits a red dwarf star, a type of star that is much smaller and cooler than our Sun, but also much longer lived. Red dwarfs make up about 75% of all stars in our galaxy and can burn steadily for trillions of years, potentially providing stable energy sources for planetary systems over timescales that dwarf the age of our solar system. However, red dwarf stars are also known for producing powerful flares that could strip away planetary atmospheres or sterilize planetary surfaces with intense radiation. Webb's detection of a substantial atmosphere around K2-18b suggests that some planets orbiting red dwarfs can maintain their atmospheric envelopes despite stellar activity. Webb's atmospheric studies extend far beyond individual planet characterization to broader questions about planetary system formation and evolution. The telescope's observations of hot gas giants have revealed atmospheric compositions that provide clues about where these planets formed and how they migrated to their current positions. Many hot Jupiters, gas giants that orbit extremely close to their host stars, show atmospheric signatures that suggest they formed much farther from their stars and then spiraled inward through gravitational interactions with other planets or with the protoplanetary disk from which they formed. The telescope has also made remarkable discoveries within our own solar system, revealing new details about the atmospheres and compositions of planets, moons, and smaller bodies. Webb's observations of Jupiter have provided unprecedented views of the giant planet's atmospheric dynamics, revealing complex storm systems and circulation patterns in the planet's upper atmosphere. The telescope's infrared sensitivity allows it to peer beneath Jupiter's visible cloud layers, revealing temperature variations and chemical compositions that provide insights into the planet's internal structure and formation history. Webb's observations of Saturn have similarly revealed new details about the ringed planet's atmospheric composition and dynamics. The telescope can detect trace gases in Saturn's atmosphere that are invisible to other instruments, providing insights into the planet's chemical evolution and the processes that drive its complex weather systems. Webb has also observed Saturn's largest moon, Titan, revealing details about its thick methane atmosphere and the complex organic chemistry occurring in its upper atmospheric layers. Recent observations of interstellar objects passing through our solar system have provided insights into the materials and processes that shaped other stellar systems. Webb observed the interstellar comet 3I/ATLAS as it passed through our cosmic neighborhood, training its infrared vision on this visitor from another star system. The comet's composition revealed chemical signatures that provide clues about conditions in its region of origin, offering a direct sample of materials that formed around stars potentially billions of years ago and trillions of miles away. Such objects are essentially messengers from distant stellar systems, carrying chemical fingerprints that reveal conditions in their regions of origin. Each interstellar visitor represents a natural space probe carrying information about cosmic processes operating throughout our galaxy. The ability to study these objects with Webb's precision provides unprecedented opportunities to understand how planetary systems form and evolve around different types of stars and under different environmental conditions. Webb's discoveries have profound implications for our understanding of cosmic evolution and the likelihood of life elsewhere in the universe. The telescope's revelation that complex galactic structures formed much earlier than expected suggests that the universe achieved the conditions necessary for planet formation and potentially life much sooner than previously thought. If rocky planets could form around early stars that were already enriched with heavy elements produced by previous generations of stellar evolution, then the cosmic real estate suitable for life might be far more abundant than we realized. The telescope's ability to analyze exoplanet atmospheres also marks the beginning of a new era in astronomy and astrobiology. For the first time in human history, we can study the chemical composition of worlds orbiting other stars, searching for signatures of biological processes and atmospheric conditions that might support life. Webb's current capabilities represent just the beginning of this revolution. Future observations will examine dozens of potentially habitable worlds, creating a comprehensive catalogue of atmospheric compositions that could reveal whether life is common or rare in our galaxy. The implications of finding biosignature gases in exoplanet atmospheres extend far beyond academic science to fundamental questions about humanity's place in the cosmos. If Webb confirms the presence of biologically produced compounds in the atmosphere of K2-18b or other exoplanets, it would represent one of the most significant discoveries in human history, providing the first direct evidence that life exists beyond Earth. Such a discovery would fundamentally change our perspective on biological processes and the likelihood that intelligence has evolved elsewhere in the universe. Webb's discoveries about early black holes have also reshaped our understanding of how these objects influence galaxy formation and evolution. The presence of massive black holes in early galaxies suggests that they played a crucial role in regulating star formation and shaping galactic evolution from very early times. These supermassive objects can influence their host galaxies through powerful jets and winds that either trigger or suppress star formation across vast regions, a process astronomers call feedback. Understanding how this feedback process operated in the early universe is crucial for comprehending why galaxies evolved into the diverse structures we observe today. Some galaxies continued forming stars at high rates throughout cosmic history, while others shut down their star formation processes relatively early and evolved into the massive elliptical galaxies we see today. Webb's observations of early galaxies and their central black holes are providing direct evidence of how this feedback process shaped cosmic structure formation. The telescope's observations have also revealed the importance of galaxy mergers in shaping cosmic structure. Webb can observe galaxies in the process of colliding and merging, events that trigger intense bursts of star formation and can reshape entire galactic architectures. These cosmic collisions were far more common in the early universe when galaxies were closer together and the cosmic web was still forming. Webb's ability to observe these ancient mergers provides direct evidence of how modern galaxies assembled from smaller components over billions of years. Galaxy mergers are not gentle processes. When two galaxies collide, their gravitational interactions can fling stars into new orbits, trigger massive bursts of star formation, and feed material into the central supermassive black holes of both systems. The resulting active galactic nuclei can outshine their entire host galaxies and influence star formation across regions spanning hundreds of thousands of light years. Webb's observations of these merger events in the early universe reveal that galaxy formation was a much more violent and chaotic process than the relatively peaceful evolution we observe in the modern cosmos. One of Webb's most scientifically significant contributions involves measuring the expansion rate of the universe with unprecedented precision. The telescope's observations of specific types of variable stars, called Cepheid variables, have refined our understanding of cosmic expansion, but they have also highlighted a persistent discrepancy known as the Hubble tension. Different methods of measuring the expansion rate yield results that disagree by about 5%, a discrepancy that persists despite increasingly precise measurements from multiple independent techniques. This tension between different measurements of the cosmic expansion rate suggests either systematic errors in our observational methods or new physics that we don't yet understand. Some possibilities include modifications to our understanding of dark energy, the mysterious component that drives accelerating cosmic expansion, or the presence of new particles or forces that affect cosmic evolution in ways not accounted for by current models. Webb's precise observations are crucial for resolving this cosmic mystery and determining whether the Hubble tension represents a crisis in cosmology or an opportunity to discover new physics. The telescope has also provided new insights into the nature of dark matter and dark energy, the mysterious components that comprise about 95% of the universe. By observing how matter is distributed in galaxy clusters and how galaxies move under the influence of invisible gravitational forces, Webb is helping astronomers map the cosmic web of dark matter that provides the scaffolding for all visible structure. These observations are crucial for testing our theories about these enigmatic components of the cosmos. Dark matter, despite comprising about 27% of the universe, interacts with ordinary matter and light only through gravity, making it essentially invisible except for its gravitational effects on visible matter. Webb's observations of gravitational lensing, where massive objects bend and distort the light from more distant sources, provide some of our best evidence for dark matter's distribution throughout the universe. The telescope can observe how light from distant galaxies is bent and magnified by intervening dark matter concentrations, creating natural telescopes that allow us to study objects that would otherwise be too faint to observe. Dark energy, which comprises about 68% of the universe, is even more mysterious than dark matter. This component appears to be driving the accelerating expansion of space itself, causing distant galaxies to recede from us at ever-increasing rates. Webb's observations of distant supernovas and other cosmic distance markers are helping astronomers understand how dark energy has influenced cosmic expansion over different epochs and whether its effects have remained constant throughout cosmic history. Webb's discoveries about stellar evolution have revealed that the first generations of stars were likely much more massive and short-lived than stars forming today. These stellar giants, perhaps containing hundreds of times the mass of our Sun, burned through their nuclear fuel quickly and ended their lives in spectacular explosions that scattered heavy elements throughout space. This rapid enrichment process helps explain how the early universe achieved the chemical complexity necessary for planet formation much sooner than gradual stellar evolution would allow. The first stars, called population 3 stars, formed from the primordial hydrogen and helium that emerged from the Big Bang. Without heavier elements to cool collapsing gas clouds, these first stars likely grew to enormous sizes before igniting nuclear fusion in their cores. When they died, their explosive deaths enriched the surrounding interstellar medium with the first carbon, oxygen, silicon, iron, and other heavy elements that would eventually be incorporated into later generations of stars and planets. Webb has not yet directly observed population 3 stars, as they likely all died billions of years ago, but the telescope's observations of very early galaxies provide indirect evidence of their influence. The heavy element abundances Webb detects in galaxies that formed just a few 100 million years after the Big Bang suggest that multiple generations of massive stars had already lived and died by that time, dispersing their nucleosynthetic products throughout the early universe. The telescope's observations of star-forming regions have also revealed the incredible diversity of planetary system architectures. Webb can observe protoplanetary disks around young stars, seeing the raw materials from which planets will eventually form. These observations show that planetary system formation is far more varied and complex than our own solar system would suggest. Some disks show evidence of planets forming much closer to or farther from their stars than traditional theories predicted, suggesting that planetary architectures can be far more exotic than astronomers previously imagined. Webb's observations of protoplanetary disks have revealed complex structures, including gaps, rings, and spiral patterns that indicate the presence of forming planets. These features result from gravitational interactions between emerging planets and the gas and dust disk from which they're forming. By studying these structures, astronomers can infer the masses and orbital characteristics of planets that are still in the process of formation, providing insights into how planetary systems like our own solar system assembled over millions of years. The telescope has also observed brown dwarfs, objects that are too massive to be planets, but not massive enough to sustain the nuclear fusion reactions that power stars. These failed stars occupy a unique position in cosmic evolution and may be more common than previously thought. Webb's infrared sensitivity makes it particularly well suited for studying brown dwarfs, which emit most of their energy in the infrared part of the electromagnetic spectrum due to their relatively cool temperatures. Webb's impact extends beyond individual discoveries to fundamental questions about cosmic evolution and our place in the universe. The telescope's revelations about early galactic complexity suggest that the processes leading to cosmic structure formation operated according to principles that are more efficient and rapid than our models predicted. This has implications for understanding how quickly habitable environments could emerge in the early universe, and whether advanced civilizations might have arisen much earlier in cosmic history than we previously thought possible. The rapid pace of early cosmic evolution, revealed by Webb, also affects our understanding of the timeline for when life might first have become possible in the universe. If heavy elements necessary for rocky planet formation became available just a few 100 million years after the Big Bang, rather than after billions of years as previously thought, then the chemical building blocks for life could have been present for nearly the entire history of the universe. This dramatically expands the potential time frame during which life might have emerged and evolved to complexity. The telescope's atmospheric studies of exoplanets are also revealing the incredible diversity of planetary environments that exist throughout the galaxy. From super-Earths with hydrogen-dominated atmospheres to gas giants with exotic chemical compositions involving metallic clouds and extreme temperature gradients, Webb is cataloguing atmospheric types that have no analogue in our solar system. This diversity suggests that planetary formation can produce worlds operating according to atmospheric and geological processes that we've never encountered, expanding our understanding of what constitutes a potentially habitable environment. Some of the most intriguing exoplanets Webb has studied are super-Earths, planets with masses between Earth and Neptune that don't exist in our solar system but appear to be common throughout the galaxy. These worlds can have a wide variety of atmospheric compositions and surface conditions depending on their formation history, orbital characteristics, and stellar environment. Some super-Earths may have thick hydrogen atmospheres that create extreme greenhouse effects, while others might have lost their original atmospheres and developed secondary atmospheres through volcanic outgassing or cometary impacts. Webb's observations have also highlighted the role of stellar activity in shaping planetary atmospheres. The telescope can observe how stellar flares and winds interact with planetary atmospheres, potentially stripping away atmospheric components or triggering chemical reactions that alter atmospheric composition over time. Understanding these star-planet interactions is crucial for assessing the long-term habitability of exoplanets and determining which types of stellar systems are most likely to maintain stable, life-supporting environments over the billions of years required for complex life to evolve. Red dwarf stars, which make up the majority of stars in our galaxy, are particularly active and can produce powerful flares that release more energy in minutes than our Sun produces in years. These flares can strip away planetary atmospheres over geological timescales, particularly for planets that orbit close to their host stars. However, Webb's detection of substantial atmospheres around planets orbiting red dwarfs suggests that some worlds can retain their atmospheric envelopes despite stellar activity, possibly due to strong magnetic fields or rapid atmospheric replenishment through geological processes. The telescope's discoveries about cosmic chemical evolution have profound implications for astrobiology and the search for life. Webb's observations show that the heavy elements necessary for rocky planet formation and complex chemistry became available much earlier in cosmic history than previously thought. This suggests that the chemical building blocks for life could have been present in the universe for nearly its entire history, dramatically expanding the potential timeframe during which life might have emerged and evolved. The early availability of heavy elements also affects our understanding of when habitable planets first became possible. Previous models suggested that several generations of stellar evolution would be required to produce sufficient quantities of carbon, oxygen, silicon, and other elements necessary for rocky planet formation. Webb's observations of heavy element enrichment in very early galaxies suggest that this chemical evolution proceeded much more rapidly than expected, potentially allowing habitable worlds to form within the first billion years of cosmic history. Webb's ability to detect and analyze the atmospheres of potentially habitable worlds represents one of humanity's most significant technological achievements. The telescope essentially functions as a cosmic laboratory, allowing us to study chemical processes occurring on worlds dozens or hundreds of light years away. This capability transforms exoplanet science from a field focused on finding planets to one capable of characterizing their environments and searching for signs of biological activity. The techniques Webb uses for atmospheric analysis involve precision measurements of how starlight changes as it passes through planetary atmospheres during transits. Different molecules absorb specific wavelengths of infrared light, creating spectral fingerprints that reveal atmospheric composition. The telescope must measure tiny changes in brightness, often less than 0.01%, and distinguish between spectral features caused by atmospheric molecules and those caused by stellar activity or instrumental effects. Webb's discoveries have also revealed the dynamic and violent nature of cosmic evolution. The telescope observes galaxies being torn apart by tidal forces during mergers, stars being consumed by black holes in events that release more energy than our Sun will produce in its entire lifetime, and massive stellar explosions that forge and disperse heavy elements throughout space. These observations remind us that the universe is far from static, and that the processes shaping cosmic structure operate through mechanisms that are often violent and dramatic on scales that dwarf human experience. Galaxy mergers, for example, can completely reshape the participating galaxies over hundreds of millions of years. As two galaxies approach each other, their mutual gravitational attraction causes them to distort and develop long tidal tails of stars and gas that extend for hundreds of thousands of light years. When the galaxies finally merge, the collision can trigger massive bursts of star formation, feed material into central supermassive black holes, and ultimately produce a single larger galaxy with properties that differ significantly from either original system. Webb's observations of the early universe have also provided insights into the cosmic conditions that prevailed during the universe's first billion years. The telescope reveals an era when star formation rates were dramatically higher, when massive black holes were rapidly growing through accretion of surrounding matter, and when galactic mergers were reshaping cosmic architecture at an unprecedented pace. Understanding these early cosmic conditions is crucial for comprehending how the universe evolved from the relatively simple state that emerged from the Big Bang to the complex cosmic web we observe today. The early universe was a much denser and more active place than the modern cosmos. Galaxies were closer together, making mergers and interactions much more common. The intergalactic medium was denser and hotter, affecting how galaxies formed and evolved. Dark matter concentrations were still collapsing and virializing, creating the large-scale structure that would eventually become the cosmic web of filaments and voids we observe today. The telescope's impact on our understanding of planetary science extends beyond exoplanets to objects within our own solar system. Webb's infrared sensitivity allows it to study the outer planets, their moons, and smaller bodies like asteroids and comets with unprecedented detail. These observations are revealing the complex chemical and physical processes that have shaped our solar system over billions of years, and providing insights into the conditions that led to the emergence of life on Earth. Webb's observations of comets, for example, reveal the pristine materials from the early solar system that have been preserved in these icy bodies for over 4 billion years. When comets approach the Sun and develop their characteristic comas and tails, they release gases and dust that provide direct samples of the materials from which our solar system formed. Webb's spectroscopic analysis of these materials provides insights into the chemical conditions that existed in the solar nebula and the processes that led to planet formation. The telescope's observations of asteroids provide complementary information about the rocky materials that went into building the terrestrial planets. Different types of asteroids preserve different chemical signatures from various stages of solar system formation, and Webb's ability to characterize their surface compositions helps astronomers understand how the distribution of materials in the early solar system influenced planetary formation and evolution. Webb's discoveries about interstellar objects like comets and asteroids visiting our solar system from other stellar systems provide unique opportunities to study materials that formed around other stars. These cosmic messengers carry chemical fingerprints that reveal conditions in stellar systems that existed billions of years ago, providing direct samples of environments that we could never otherwise study. Each interstellar visitor represents a natural space probe carrying information about cosmic processes operating throughout our galaxy. The chemical composition of interstellar objects can reveal whether their parent stellar systems had different heavy element abundances, different planet formation processes, or different stellar evolution histories compared to our own solar system. By studying these visitors, astronomers can begin to understand the diversity of planetary system formation processes that operate throughout the galaxy and gain insights into how common or rare the conditions that led to life on Earth might be. The telescope's observations have also revealed the incredible precision and sensitivity required to detect and characterize potentially habitable exoplanets. The chemical signatures that might indicate biological activity are often extremely subtle, requiring measurements that push the boundaries of current technology. Webb's success in analyzing exoplanet atmospheres demonstrates humanity's growing capability to address fundamental questions about life's prevalence in the universe through direct observational evidence rather than speculation. The search for biosignature gases in exoplanet atmospheres requires distinguishing between chemical signatures produced by biological processes and those resulting from non-biological chemistry. On Earth, oxygen is a biosignature because it's highly reactive and would quickly disappear from our atmosphere if it weren't continuously replenished by photosynthesis. However, oxygen can also be produced through non-biological processes like photodissociation of water vapor, so detecting oxygen alone wouldn't definitively prove the existence of life. More promising biosignature gases include those that are thermodynamically unstable and unlikely to be produced in large quantities through non-biological processes. Dimethyl sulfide, the compound tentatively detected in K2-18b's atmosphere, is one such biosignature because it's primarily produced by biological processes on Earth and would be rapidly destroyed by atmospheric chemistry if not continuously replenished. Other potential biosignatures include phosphine, ammonia, and various organic compounds that would indicate active biological metabolism. Webb's discoveries about early galaxy formation have implications that extend beyond astronomy to fundamental physics and cosmology. The rapid assembly of massive galactic structures in the early universe suggests that our understanding of how matter behaves under extreme conditions might be incomplete. These observations are prompting cosmologists to reconsider basic assumptions about dark matter interactions, stellar formation efficiency, and the processes that drive cosmic structure formation. Some of the most massive early galaxies Webb has observed appear to contain more stars than should be possible given the amount of time available for star formation. If confirmed, these observations might require modifications to our understanding of how efficiently gas can be converted into stars, how massive the first generation of stars could become, or how quickly supermassive black holes can form and influence their host galaxies. The telescope's ability to observe the universe across vast ranges of cosmic time essentially allows astronomers to study cosmic evolution as an experimental science. By comparing galaxies at different epochs, Webb can directly observe how cosmic structure has changed over billions of years. This temporal perspective provides insights into cosmic evolution that cannot be obtained through any other means, making Webb not just a telescope, but a time machine that reveals the universe's history. Webb's atmospheric studies of exoplanets are also revealing the complex interplay between stellar evolution and planetary environments. The telescope can observe how planets orbiting stars of different ages and types develop different atmospheric characteristics, providing insights into how stellar properties influence planetary habitability over time. These observations are crucial for understanding which types of stellar systems are most likely to host life, and for prioritizing targets for future searches for extraterrestrial intelligence. Young stars tend to be more active than older ones, producing more frequent and powerful flares that can affect planetary atmospheres. However, young stellar systems also tend to have more massive protoplanetary disks that can shield forming planets from stellar radiation. As stars age and settle into stable main sequence burning, their activity levels typically decrease, potentially creating more favorable conditions for atmospheric retention and biological evolution. The telescope's discoveries have also highlighted the importance of technological advancement in driving scientific discovery. Webb represents the culmination of decades of engineering innovation, from the development of ultra-sensitive infrared detectors that must operate at temperatures just a few degrees above absolute zero to the deployment of a mirror system that must maintain precise alignment despite operating in the harsh environment of space. The telescope's success demonstrates humanity's growing capability to build instruments that can address fundamental questions about cosmic evolution and our place in the universe. The technologies developed for Webb have applications beyond astronomy. The precise pointing and stabilization systems required to keep the telescope aligned with distant targets have applications in satellite technology and space navigation. The sensitive infrared detectors developed for Webb's instruments have potential applications in medical imaging, environmental monitoring, and national security. The advanced materials and manufacturing techniques used to construct Webb's mirror segments and sunshield are finding applications in other fields requiring lightweight, high-precision structures. As Webb continues its mission over the coming decade, its discoveries are reshaping our understanding of cosmic evolution, planetary science, and the potential for life throughout the universe. The telescope's revelations about early galactic complexity, exoplanet atmospheres, and cosmic chemical evolution provide insights that will influence astronomical research for decades to come. Each observation adds new pieces to our understanding of how the universe evolved, from the relatively simple conditions that emerged from the Big Bang to the complex cosmic ecosystem we observe today. Future observations planned for Webb include detailed studies of potentially habitable exoplanets, continued surveys of the early universe to understand galaxy formation and evolution, investigations of stellar nurseries to understand how planetary systems form, and studies of objects within our own solar system to understand the conditions that led to the emergence of life on Earth. Each of these research programs has the potential to make discoveries that could fundamentally change our understanding of cosmic evolution and our place within it. The implications of Webb's discoveries extend far beyond academic astronomy to fundamental questions about humanity's cosmic significance. The telescope's revelations suggest that the universe achieved complexity much earlier than expected, and that the conditions necessary for life might be more common than previously thought. If Webb's tentative detection of biosignature gases around K2-18b is confirmed by future observations, it would represent one of the most significant discoveries in human history, providing the first direct evidence that life exists beyond Earth. Such a discovery would have profound implications for biology, philosophy, and our understanding of our place in the cosmos. It would suggest that the chemical processes that led to life on Earth are not unique, but represent a more general phenomenon that occurs throughout the universe under appropriate conditions. This would fundamentally change our perspective on the significance of biological evolution and the likelihood that intelligence has evolved elsewhere in the galaxy. Webb's ongoing mission represents humanity's most ambitious attempt to understand our cosmic origins and search for life elsewhere in the universe. The telescope's discoveries are not just expanding our knowledge of astronomy, but are addressing fundamental questions about whether life is common or rare in the cosmos, how quickly habitable environments can emerge after planetary formation, and what types of worlds are most likely to support the complex chemistry necessary for biological processes. The next decade of Webb observations promises to be even more exciting than its first few years of operation. As the telescope completes deeper and more comprehensive surveys of the early universe, characterizes the atmospheres of dozens of potentially habitable exoplanets, and continues to study stellar formation and planetary system evolution, it will undoubtedly reveal additional surprises that will further reshape our understanding of cosmic evolution. Webb's legacy will ultimately be measured not just in the individual discoveries it makes, but in how it changes our fundamental perspective on cosmic evolution and the potential for life throughout the universe. The telescope has already demonstrated that the universe is far more complex and dynamic than we previously imagined, and its future discoveries will likely continue to surprise and challenge our understanding of cosmic evolution, stellar formation, planetary system architecture, and the conditions necessary for life. The James Webb Space Telescope has fundamentally transformed our understanding of the universe in just a few short years of operation. Its discoveries about early galactic evolution, exoplanet atmospheres, stellar formation, and cosmic chemical evolution have challenged basic assumptions about how the cosmos works and have opened entirely new avenues of scientific investigation. As the telescope continues its observations over the coming decade, it will undoubtedly reveal additional surprises that will further reshape our understanding of cosmic evolution and our place within the vast, complex, and dynamic universe we call home. Beyond the discoveries themselves, Webb has become a symbol of what international collaboration and persistence can achieve. The telescope took decades of planning, engineering, and problem-solving, involving contributions from NASA, the European Space Agency, the Canadian Space Agency, and countless engineers and scientists around the world. Its success is not just a triumph of technology, but also a demonstration of what humanity can accomplish when we pursue shared goals that transcend borders. Webb also acts as a bridge between generations of astronomers. It builds upon the foundation laid by the Hubble Space Telescope, which revolutionized our understanding of the cosmos for more than 3 decades. Yet Webb's ability to see farther and deeper has already surpassed Hubble in many ways, opening up entirely new frontiers of exploration. The two telescopes together form a scientific partnership, with Hubble continuing to provide optical and ultraviolet insights, while Webb extends our vision into the infrared. This complementary relationship ensures that our picture of the universe grows sharper, richer, and more complete. As the scientific community analyzes Webb's data, textbooks are already being rewritten. The timeline of cosmic evolution looks different than it did only a few years ago, with galaxies forming sooner, stars assembling faster, and chemical complexity appearing earlier than expected. These shifts remind us that science is not static. It is a living process of discovery, refinement, and surprise. Every Webb observation is not just an endpoint, but a starting point for new questions, new theories, and new missions that will follow in its path. In the decades ahead, the impact of Webb will ripple outward. Future telescopes like the Nancy Grace Roman Space Telescope and the European Extremely Large Telescope will build on Webb's findings, targeting the most promising candidates for habitable worlds and probing the deepest mysteries of dark matter and dark energy. In that sense, Webb is not just a tool of discovery, it is a guidepost pointing us toward the questions that the next generation of explorers must answer. Perhaps Webb's greatest achievement is that it restores a sense of wonder at a time when the universe can feel both familiar and overwhelming. By showing us galaxies glowing in the first few 100 million years after the Big Bang, by revealing chemical fingerprints in the atmospheres of distant exoplanets, and by hinting at the possibility of life elsewhere, Webb reminds us that we are part of something vast, ancient, and ongoing. Its images are not just data points, they are windows into a story that stretches across billions of years and countless worlds. The James Webb Space Telescope is more than an observatory. It is a milestone in human curiosity, a beacon of our collective drive to look outward, and a testament to the belief that knowledge itself is worth striving for. Whatever surprises await in the years to come, Webb has already secured its place in history, not only as a scientific instrument, but as a symbol of humanity's quest to understand the cosmos, and, in doing so, to better understand ourselves. In the end, the James Webb Space Telescope is more than just the sum of its mirrors, instruments, and engineering marvels. It is the embodiment of a question that has driven humanity since the dawn of thought. Where do we come from, and are we alone? Every beam of light it collects is a message from the past, a whisper carried across billions of years of cosmic history. By decoding those whispers, Webb allows us to piece together the unfolding story of the universe, from its fiery beginnings to the delicate balance of worlds that might cradle life. Its legacy will not be measured only in the galaxies catalogued, the exoplanets analysed, or the molecules detected, but in the shift it creates in our collective imagination. For centuries, our species has looked to the night sky and wondered what lies beyond. Now, with Webb, those ancient questions are meeting modern answers. The telescope has already shown us that the universe is not sparse or simple, but fertile with complexity, rich with unexpected structure, and alive with possibilities we are only beginning to comprehend. What Webb teaches us is that discovery is not a destination, but a horizon, one that moves farther away the closer we approach. Each new image raises questions as profound as the answers it provides. Why did galaxies form so quickly after the Big Bang? How widespread are the building blocks of life? Could habitable conditions be the rule rather than the exception in the galaxy? These are not questions for scientists alone, but for humanity as a whole, because their answers will shape how we understand our place in existence. Perhaps the most remarkable truth is that Webb's revelations belong to everyone. The light it gathers does not speak only to astronomers. It speaks to all of us, reminding us that Earth is a single point in an endless sea, and yet on that point we have built the tools to see beyond ourselves. Its images, shared instantly with the world, belong as much to a child gazing in wonder as to a researcher writing equations. In this way, Webb unites us, not through politics or power, but through curiosity, awe, and the timeless human desire to know. As the telescope continues its mission, its discoveries will echo through classrooms, inspire new generations of explorers, and guide the direction of science for decades. But beyond the scientific milestones, Webb's greatest contribution may be the perspective it offers, that we are part of a vast interconnected cosmos, one whose story is still being written. With every observation, we are not just learning about galaxies and exoplanets, we are learning about ourselves, about the improbable journey that led to our existence, and about the possibilities that still await in the infinite expanse. The James Webb Space Telescope is not the end of exploration, but the beginning of a new chapter. And as its golden mirrors continue to unfold the hidden beauty of the universe, they reflect back to us the most powerful truth of all, that in seeking the cosmos, we discover what it means to be human. As we close this journey through the James Webb Space Telescope's discoveries, it is worth remembering what makes this mission so extraordinary. Webb is not simply a machine floating 1,000,000 miles from Earth, it is the culmination of decades of human ingenuity, sacrifice, and persistence. Thousands of scientists, engineers, and visionaries came together with one shared goal: to extend our vision deeper into the cosmos than ever before. And already, Webb has delivered more than anyone could have imagined. In only a few short years, it has pulled back the curtain on the early universe, showing us galaxies that formed just a few 100 million years after the Big Bang. It has revealed worlds orbiting distant stars with chemical fingerprints of water, methane, and carbon dioxide. It has given us the first hints, still unconfirmed, but tantalizing, of molecules that could point toward life. Each discovery carries us closer to answering questions that have haunted humanity since the beginning. How did we get here, and are we alone? But Webb's importance extends beyond astronomy. Its technology is shaping fields as diverse as medicine, environmental monitoring, and engineering. Its images have captured the imagination of people everywhere, sparking wonder in children who will grow up to be the next generation of explorers. And its data will serve as the foundation for decades of research, inspiring new missions, new telescopes, and new ways of seeing the universe. The beauty of Webb is that it reminds us science is never finished. Each answer leads to deeper questions. Each image reveals hidden complexities. Each breakthrough sparks new mysteries. Why did the universe grow complex so quickly? How common are habitable environments? Could life have arisen not just here, but across countless other worlds? Webb cannot answer all of these questions, but it is pointing us toward the right places to look. In the decades ahead, its discoveries will ripple outward, guiding future telescopes and inspiring discoveries far beyond what we can predict today. Yet even now, its greatest achievement may be the perspective it gives us. We are reminded that Earth is just one small world orbiting one ordinary star, and yet here, on this fragile blue planet, we have developed that appear across billions of years and billions of light years. That perspective is humbling, but it is also deeply inspiring. The James Webb Space Telescope is more than a scientific tool. It is a mirror reflecting our own curiosity, our determination, and our place in the cosmos. It shows us that the universe is not distant and abstract, but connected to us in profound ways. Its story is our story, written across time and space in the light of ancient stars. And so, as Webb continues its mission, it leaves us with one simple truth. The universe is vast, complex, and full of mysteries. But by daring to look deeper, to reach farther, and to imagine more, humanity has taken one of its boldest steps yet into understanding the story of creation and our place within it.